Hey folks, Joe Miliano here. I'm excited to make this video. Arbor Scientific reached out to me and they offered to give me one of their brand new Lenz's Law demonstration kits if I made a video, gave an honest review of the product. It's a very cool product, very excited to show you what it does. And so let's go ahead and get started with that, shall we? So first I want to show you everything that comes in the kit here. So bringing you around, here's what we've got. We got an air core solenoid, very excited to have an extra one of these. Lots of stuff you can do with them when it comes to magnetism demonstrations. A few wires to connect stuff. This plate with a circuit built into it, this is really cool. This is what's new for them compared to other demonstrations. This green and red LED at the top are very cool, and they give a nice visual way to show which direction the current is flowing in your air core solenoid at different times when a magnet is dropped into it. And I'll show you that in a bit, but this is very cool. It's a very simple circuit there. They've got just the two LEDs, and we can see how it's wired on the back there. And then the solenoid straps in to that Velcro. Another thing I'm very excited about here is this gigantic neodymium magnet. And I've put a little north-south pole sticker on there so we can see which pole is which, but this is very cool. This copper cylinder here that's hollow, nice thickness to it though. And last but not least is this plastic, is it in the video? This plastic tube here. Now what's really cool about it is that this ring is made so that it fits right over that plastic tube. And I've got a rubber band here to hold it up. And so that's our whole setup. And I'm going to show you what a progression might look like when you're doing this with students. So let me put the camera and set that up appropriately in the right spot. It's a little far away. Let's see, that looks pretty good. All right. So, very cool demonstration to start us off here. So, this one you're probably familiar with, right? I've got my giant neodymium magnet, and I'm going to drop it through the tube. And the box that the magnet came in has a foam cushion to catch the magnet after I drop it. So I take this and place it underneath, which is a little bit off frame, but that's okay. And I'm gonna drop this in North Pole first. And we're gonna watch what happens. What I really love about this version of this demo is that it's not an entirely copper tube. We see it go fast through the plastic. It will slow down as it goes through here, which is the eye-catching part for students. And it speeds up again in the plastic. So here we go. Here's that drop. 3, 2, 1. Very cool. I dropped that in North Pole first. Let's reverse it and do South Pole first now. And drop it through. And again, we have it slow down during the copper. It doesn't matter which pole, north or south, goes first. And you want to set this up with students, ask them some questions, right? Ask them to make some predictions, what they think will happen, especially after that flip. Do you think it will slow down regardless of pole direction? Do you think it will speed up? And then that leads into a conversation of what's going on. And we can start talking about Lenz's law. So in this case, as the magnet falls through, the changing magnetic field in this copper will introduce eddy currents. And those eddy currents are electrons swirling around in the copper, and those will be induced in such a way that the magnetic field generated by those moving electrons is opposing the change in magnetic flux through that tube. It's a complicated explanation. You want to do lots of demonstrations with this idea, but it's a great hook to get them interested in what's going on. But as those eddy currents create the opposing magnetic field, that magnetic field exerts a magnetic force which slows the fall of the neodymium magnet. So you got that qualitative idea, that conceptual idea, but now we want to start looking and answering some more questions. The next step in this progression would be to look at, all right, in which direction is the current flowing? And that's where we replace our copper tube with our air core solenoid. And I'm going to strap it into our circuit here. Now, because the solenoid is not as thick as just this copper cylinder, the neodymium magnet does slow down, but not nearly as much. But the trade-off is that we can get some nice readings for the direction the current flows. So this is strapped in now, and diameters of all these things are such that this fits right in. Then you watch it drop through, and I'll demonstrate the, nope, that's not what I want. I want the magnet, drop our magnet through our tube, and it doesn't noticeably slow down, but it does slow down some. But in particular, here's the cool part about it, is I can grab the 2 banana plugs they gave, and we can plug one end of our air core solenoid into this top part of the circuit. We can plug the bottom, or the other end of our air core solenoid into the bottom here. And we have these 2 LEDs then. Right now I'm going to turn this switch to off. That takes this red LED out of the circuit. And the green one will turn on anytime there's current turning through the solenoid. I like to emphasize at this point when I'm teaching that there are no batteries involved. This copper itself is not magnetic, right? In fact, I probably should have shown that earlier. The copper is not magnetic. No batteries, no power sources, anything like that. But when I drop my magnet through here, this green LED will turn on. It's a quick blink, but it is there. I'll make a second video where I get some high-speed footage of that drop. You should do that North Pole, South Pole, see we get a blink each time. After you've shown that we're going to run some current through there to turn the LED, this is where adding the red LED really makes a neat effect. So far, it hasn't mattered if we go north first or south first. But if we go north first here, we can watch, and again, I'll do this in high speed in a separate video, but we can see that we go, the order differs. The red turned on first, and then the green. That corresponds to current going in one direction around the coils of that wire. If I flip my magnet and do south pole first through our tube, the opposite was true. Green turned on first and then red, and that corresponds to current going in the other direction around our solenoid here. So now we can see, so now we can start drawing some pictures, get into a discussion. Why is it that the direction changes depending on if it was North Pole or South Pole first? Right, as the North Pole falls, if we go North Pole first, we need to generate a field that opposes a North Pole. That's going to be an upward field. Right-hand rule tells me that we're curling around in the counterclockwise direction from the bird's eye view. As the South Pole is falling in, we want to oppose a South Pole, which means the magnetic field from the generated current has to point down, and that's going to be current in the other direction. And then as it falls through to the other end, the reverse is true. Rather than trying to push the magnet up as it falls, we're trying to pull the magnet up as it goes through the second half of its fall. And that pull up, the current has to reverse direction. So this is all neat. The last thing you can do with this, which is the next step, I think very cool as well, is we can upgrade this whole thing from just looking at blinks to taking some voltage measurements. So we can take these banana plugs out of the circuit and instead put in a voltage probe. Now this did not come with the kit. I'm using a vernier differential voltage probe here, but they come with these nice alligator clips. This is the probe, and so I can put my red alligator clip at one end, my black alligator clip at the other. Maybe. There it is. And it's plugged in to this computer here. I'll show you the graph in a moment, but it's measuring the potential over time. I do need to quickly up the sampling rate. 10 samples per second is not enough. Let's do 100 samples per second. That ought to be good. I'm going to change the time interval to end after, let's say, 5 seconds, not 18 seconds. All right, so I'm going to do this North Pole first, drop it through. I'm going to press collect on my data collection here. Collect, drop. Stop the data collection. I'm going to show you what I got. All right, so here we have the quantitative piece now. Here is our voltage, our potential difference as a function of time. We can zoom in on that spike. And we can see we had a positive potential for the first half of the magnet's fall, negative potential for the second half. If I upped the sampling rate more, I probably could have gotten a smoother curve than those jagged triangles. But that was North Pole first, up and then down. Let's reverse the polarity now of our magnet so that the South Pole drops first. And if we do that, there you go. Collect data, South Pole first. Stop. Zoom in just on the relevant portion of the graph. Let me grab you again. And we've got ourselves a negative potential first and then a positive potential. And so we can change that. So really neat device, really neat progression that you can do here from the conceptual, the magnet slows down in the thick piece of copper all the way to the measured quantitative potential difference, reversing direction halfway through the magnet's fall. Really neat device, excited to have it. If you have any questions for me, please let me know.